Okay, we are ready to go. Good morning, everyone, and welcome to the Foreign Correspondents Club of Japan. My name is Dennis Normile, and I'll be the moderator this morning. I also have something of a connection with these two researchers because I'm the correspondent for Science magazine, and they've both published scientific papers in Science. Before we get started, please join me in double checking that your phone is either off or on manner mode. And I'd like to thank you all for turning out in such terrible weather. We're very honored to have Japan's newest Nobel laureates with us here this morning. To my far right down the table is Dr. Shimon Sakaguchi, who is a laureate for physiology or medicine. He's also distinguished honorary professor, the Immunology Frontier Research Center at the University of Osaka. Immediately to my right is Susumu Kitagawa. He is the chemistry laureate this year. He is an executive vice president at Kyoto University. I will leave it to them to talk a little bit about their research, and then we'll hopefully hear some comments about how they see the state of research and development in Japan. We'll first hear from Dr. Sakaguchi. We tried to decide who should go first, and then we decided that we should follow the order that the Nobel Prizes are announced. Dr. Sakaguchi was announced first, and Dr. Kitagawa was announced second. So we'll start with Dr. Sakaguchi. Onegaishimasu.
Thank you, Dennis, for kind introduction. And then also thank you for inviting us here today. I'd like to talk about what we've done and what was appreciated by the Nobel Assembly for a Nobel Prize in physiology or medicine. So just briefly, let me introduce to you what we have done. So this is the title of my Nobel lecture, Regulatory T cells for immune tolerance, discovery and clinical prospects. So the award was awarded to 3 people, including me, Mary Blanco and Fred Ramstel. And then, so it was awarded for the discoveries concerning peripheral immune tolerance. So let me first talk about what is immune tolerance. So our immune system, which protect us from invading microbes, such as viruses and bacteria. So the immunology has developed for fighting against such pathogenic pathogens. So how we can protect from them by vaccination or other ways of fighting against microbes. So the immune system has it can react with diverse antigens, high antigen specificity, and immunological memory, and a potent mechanism of antigen elimination, including T cells, which can destroy the virus-infected cells, and an antibody, which can neutralize viruses. So the very potent mechanism for protecting us from microbes. But on the other hand, if the immune system turn against our own tissue, self, then the autoimmune disease happens. Or under organ transplantation setting, if the organ rejection happens because of these potent mechanisms, it's very difficult to stop the rejection. So how the immune system controls the immune responses not to react with self, that is called the immune self-tolerance. And Paul Ehrlich, he's a Nobel laureate in 1908, and he invented a magic bullet for microbes. And then he also he was a great immunologist. And then in his paper published in the at the turn of the century, he says there is a mechanism for the immune system not to react with self. That is important, very important. And then, imagine at that time the vaccination, for example, Shibasaburo Kitazato and then the Emil von Behring, they are making the anti-serum against the microbes. So they are immunizing the horses by such the microbial products. But if you immunize the horse with his or its own blood cells, no responses. But if you immunize one horse by the other horse's blood, and you'll see the antibodies against the red blood cells. And so somehow they thought that there must be a mechanism in the immune system to prevent the anti-self immune responses. And what the mechanisms have been, that question has been the great challenge for immunologists for more than 1 century. So there are many autoimmune diseases. As you may know, rheumatoid arthritis, or type 1 diabetes, or multiple sclerosis in the brain, and then many others. And then it is estimated that 88% of the population is afflicted with some sort of autoimmune disease. What's the mechanism? First, it was proposed that such dangerous cells, lymphocytes, may be deleted. They'll die when they are produced. So it is called deletion. So second, the mechanism they proposed, that was inactivation. They don't die, but then become inactivated. So they are present, but they don't react with self. And third mechanism which we are working on, that is even normal individuals, they may harbor the potential hazardous lymphocyte against self. But then there is another population which controls the expansion or activation of such dangerous lymphocyte. It is called suppression. So a key question for many years, that is which mechanism can explain the mechanism of autoimmune diseases in humans. So what we found is that this mechanism, if you alter this mechanism, really you'll see the development of these various autoimmune diseases in various organs. So what we've done in the past, that is on this slide. So just simple experiments. So there is the normal mouse, here spleen. You can make a splenic lymphocyte suspension. And if you remove certain population of cells, and then transfer to T cell deficient mice. And so T cells are depleted, but B cells, antigen presenting cells, other immune cells they are intact. So if you transfer, if you presume that certain population is really suppressing the anti-self immune responses, and then if you after depletion, and if you transfer to them, these mice, recipient mice, may develop various autoimmune diseases. That was indeed the case. So the various markers, using various markers, we ended up with this marker, CD25. So this is the flow cytometry data. So each dot means each lymphocyte. So here, this means CD4 positive and CD25 positive cells here, around 10% of CD4 positive cells. And if you can eliminate and deplete them, as shown here, and then transfer the remaining cells into these mice. They spontaneously develop really the autoimmune diseases very similar to what we see in humans. So that is the basic mechanism, and then we found that the marker, and then showed that there is definitely the T lymphocyte which are specialized for immune suppression. We call them regulatory T cells. So that was published in 1995. And then this time, the Nobel Assembly appreciated this paper, which defined the regulatory T cells in the immune system. And then also the two other Nobel laureates, the Mary Blankoff and Fred Ramstel, they characterized the gene which is responsible for the human disease called IPEX syndrome. I means immune dysregulation. P means the polyendocrinopathy. So various autoimmune diseases in the endocrine organs happens, especially type 1 diabetes. And enteropathy, this is inflammatory bowel disease, and disease gene is on the X chromosome. So it is called IPEX syndrome. So they clone the gene by positional cloning. And then, so this disease, it's a very rare disease, but conceptually it's important because of this one gene defect, type 1 diabetes happens more than 80%, and the thyroiditis more than 70%, and then also various other autoimmune diseases happens. So type 1 diabetes, especially Caucasians, the more than 80%, and inflammatory bowel disease happens almost all the patients. So after milk feeding by mother, and then intestinal and the microbes now they develop, and then the inflammatory bowel disease, which is the overreaction to intestinal microbes, and that happens. And then very severe allergy. So the baby start to have an oral feeding, and then immediately you'll see a food allergy, almost 100%. So one gene defect, if you characterize, or if you characterize the function of this gene, you may be able to understand not only autoimmune disease, but also allergy and inflammatory bowel disease. So they found the gene, it is called the FOXP3, and then but they didn't know how this gene defect causes various diseases. And then we found 2 years later, in 2003, that the FOXP3, this gene is really expressed by regulatory T cells, which is CD25 positive population in the spleen, also in the thymus. So conceptually, then we can say that the anomalies of regulatory T cells can be responsible for human diseases, including autoimmune disease, allergy, and inflammatory bowel disease. So these findings altogether, now our understanding is on this slide. So potentially dangerous lymphocytes against self, they are present, but they are controlled, like the rocks under the sea. And then, of course, the immune system can respond to non-self, such as bacteria and then viruses. And if you remove regulatory T cells, now you see common autoimmune diseases such as type 1 diabetes or the thyroiditis happens. And at the same time, the immune responses against non-self, it can be enhanced. So you'll see the inflammatory bowel disease or allergy. So this means that the border between self and non-self, that is not fixed. So the potentially hazardous autoimmune T lymphocytes are present in every healthy individual, but under dominant suppression by Treg. So conceptually, this changes the paradigm, because previously people thought that such dangerous lymphocytes are all gone, depleted. But no, it's not the case. They are present, but they are controlled. And then the border between self and non-self is not fixed here. It can be movable. And so this means that reducing this border, immune responses can be enhanced. So it's good for tumor immunity, anti-cancer immunity. And if you raise the threshold, then you can induce organ transplantation. So from these findings, now in the clinic, targeting regulatory T cells, that is useful for evoking effective tumor immunity and then inducing transplantation tolerance and then treating the various autoimmune and then other inflammatory diseases. So in passing, there's one nice perhaps journalistically interesting paper here, published by Jean-François Bach, the French immunologist. So he shows that in developed countries like the United States or Europe, and then maybe Japan, so during the 50 years from 1950 to 2000, the various infectious diseases became controlled. For example, rheumatic fever, measles, mumps, tuberculosis, all effectively controlled. But on the other hand, there are some diseases which have became more frequent than before. They are autoimmune diseases, for example, type 1 diabetes or multiple sclerosis, or inflammatory bowel disease, such as Crohn's disease, or allergy, such as asthma. So these diseases, now they are increasing also in Japan. And then these diseases are really what we see after manipulating the regulatory T cells, reducing or depleting regulatory T cells in humans and also animals. So we believe that the society become clean, the cleaner, and the more frequent these diseases are. And so it is called the hygiene hypothesis. And then perhaps regulatory T cells, they may become weaker when they are not much stimulated in the hygienic society. And then that is a bit dangerous for causing, dangerous because they may be responsible for causing these diseases. So the regulatory T cells, first we proposed this concept 1982, and then not much appreciated. And then at the 1995, we defined that population with a definite cellular marker called CD25. So the 10% of CD4 positive cells, they are the suppression specialized population. And then in 2001, the Mary Blanco and Fred Ramstel, they showed the gene, cloned the gene called FOXP3. And then the publication of regulatory T cells very rapidly increased. And so as shown here. And then these 20 years or so, we have a good understanding of how regulatory T cells, they control the immune responses. And then also how they can be applied in the clinic to treat cancer, autoimmune diseases, inflammatory bowel disease, and also other immunological diseases. So this is the last slide of my talk. So now the FOXP3 positive, CD25 positive regulatory T cells, they are controlling the various, suppressing the various immune responses. And then the anomaly of this population can be responsible for autoimmune diseases, allergy, or immunopathological diseases such as the inflammatory bowel disease. By increasing them, you can induce the organ transplantation, transplantation tolerance, or fetal-maternal tolerance to prevent spontaneous abortion. And then also by reducing them, you can enhance immune responses because suppression become attenuated. And so it's good for tumor immunity or controlling chronic viral infection. And so this kind of the clinical trials are now underway. Maybe more than 200 clinical trials are ongoing now. So we hope that the improving the ways of targeting Treg to control various physiological and then pathological immune responses, and then control the human diseases, and that's we hope to do in future. So thank you very much for your attention.
Okay. Dr. Kitagawa.
Okay. Good morning. Thank you very much for inviting me to be here. So I'm talking about the materials from the chemistry side. So in 19th century, the people created new technologies that consume a lot of energies. People use coal as energy resource. In 20th century, as you know, the liquid petroleum are used. What about the 21st century here? And we think the gas substances are very important for our future and present also. So these small molecules, in the ambient condition, they are gas state besides water. But water also shows the vapor in a sort of the gas state. So these gas substances are strongly correlated to the environment and the natural resources and energy, even in the case of the life. They are very important. However, humankind is still not in control of gases because gas is very difficult to handle. So the current society, our planet, our society is dependent on the underground resources. In particular, in the petroleum, is very important for even now for very important materials. From this, we can produce a lot of things, as you know. And the depletion of the underground resources and the global warming become big concern. So what we should do in the future? So the one answer is to use ubiquitous resources. So that is independent on the underground resources. For instance, in the air contains a lot of the elements, the carbon, oxygen, hydrogen, nitrogen, and so on and so forth. So, but if we can use these gas substances and produce many important materials, it's fantastic. But still, this is not a reality. Why so? Because gas substances diffuse very fast, and they are invisible. And in several gas substances have a short life and also toxic, very difficult to handle. So to handle these substances and develop the science and technologies, we need to have a new type of porous materials. By using porous materials, we can separate the gas substances to get the target gas species, and also the store and concentrate gas substances, and most importantly, we convert these gas substances to the useful materials. So all processes, to get all processes, we need to have the very sophisticated, advanced porous materials. So let me tell you the history, the human history. In the 3,500 years ago, the Egyptian era, the people already used the porous materials, that is charcoal or the activated carbons. 18th century, inorganic materials were found from the natural stones. But still, this is the underground resources. However, in the 19th century and to the 20th century, artificial synthesis of zeolites, this is the zeolites, artificial zeolites was made. So this is the reason why the modern current the petroleum industries are well developed by these zeolites. So what is interesting is in the Alfred Nobel, he set up this Nobel Prize, but he invented the dynamite. So the dynamite contains the very explosive nitroglycerin, but he used the porous materials, that is diatomite in Japanese, in the case odo. So by using this, he invented the very useful dynamite. So in the Nobel history, just the porous materials are very important. So this is the target. That's the efficient separation, storage, and conversion at low energy. That's very, very important. So today the talk, I will talk about the porous metal complexes materials. So this achievement was recognized by Nobel as a Nobel Prize. This is for the development of metal organic frameworks. So these three are Nobel laureates. So let me tell you very briefly about the MOF materials. MOF materials in nanoscale, just like this kind of structure. So, but big issue, how we can make this kind of very beautiful, regular nanoscale structure? We are very lucky because in the chemistry, there is a very important bond, that is coordination bond. This is this bond connecting blocks, that is the metal ions in organic molecules in nanoscale, just like this. So we can get this type of the porous structure, porous materials. This is a crystalline form, very beautiful crystalline form. So this has this kind of the nanochannels, the gas molecule, for instance, in this case is the CO2, are incorporated in the cavities like this. Okay, so the time is limited. Just at the beginning, I told you how we can handle the gas substances by using the MOF materials. MOF materials is very we can design these MOF materials and easily synthesize the different type of the size and the shape of the pores. So the capture the target molecule, for instance, CO2 from the air, and then concentrate, store the CO2, and convert the CO2 using the renewable energy and the water. Water contains hydrogen. So we produce the very important fuels, foods, medicine, and the commodities, and so on and so forth. In the case of fuels, once this is the combusted into the air, but from the air we can capture again the target CO2, and this is a very important cycling system. So this is our target, one of our target. So we think this air is invisible gold. So thanks to these properties, there are so many functions, properties were found, so many. So no time to tell you, but you have the copy of this one, you can check it. So nowadays, there are 55 the very visible startups in the world. So the startups are very big contribution to the transfer of MOF materials of society. So that because they can make a scale up of more materials and also the cost down these materials. For instance, in the Kyoto University has the startups, Atomis. Atomis already commercialized the MOF materials in collaboration with the other companies. The first one is this one is Nippon Fuso. This is coating, MOF coating to stabilize the coating system. And the Ohara Palladium, excuse me, Ohara Palladium, and also the MOF filter. And also the Daikin and the Atomis also their own mission, the storage of the gas substances, and using the cubitan. So this is very busy slides, but you can check it. This is produced by the Ohara Palladium, and in particular the instant deodorant, the filter is very useful for our daily life. And this is the new mat in the startups from Northwestern University. This is one of the production. This is the gas mask. And the other one is Atomis, the collaboration with the Daikin, and they produce the just recycling of the fluorocarbons. And another one is the stored methane in the very compact and the light the vessel that we call cubitan. And so also not only the methane but also the other gas substances, the nitrogen, oxygen, helium, and so on and so forth. So finally, let me tell you about the target, the CO2. This is a kind of the CO2 contained the gas system. In case in the biogas, the biogas contains 50% CO2, highly concentrated CO2, but syngas 30%, and natural gas and 5% CO2. And for instance, in the atmosphere of the spaceship, in the CO2 concentration control is very important for the human. But the concentration limit 5,000 is still a small number. But air, that is the 400 ppm, very, very diluted. How we can separate to get CO2 in such a dilute condition? So we need to have the new type of materials. So in the world, the various companies working on the CO2 capture. This is one example in the Canada and the Svante, and set up this kind of the CO2 capture of the flue gas in the cement company. And also in Japan, we have a collaboration in the Kurasas chemical, and we set up the MOF materials. So this is the MOF pellets, and this MOF pellets equipped in the column, and this is the small pilot plant in the second phase, and we are checking this kind of CO2 and the capture, and this is supported by NEDO project. So this is I think the summary of so you can see you can catch the outline of the startup, how startups contribute to to contributing to the society. Yeah, left column is just functions of materials, and middle in the details of this kind of the commercialization. And so I told you there are 55, at least 55 startups. These startups are strongly correlate to this kind of the functions. So once again, I think the AI is invisible gold. So we still investigating the very efficient MOF materials for the gas capture, in particular in the air, and convert to these materials. This is the near future our plan. Thank you very much for your kind attention.
Okay, thank you to both our guests. We'll move right into Q&A. We'll start with questions from the working press. And we'll take one question per customer. Maybe if we have time, we'll go back for a second round. And come to the microphone and please give your name and affiliation. We'll start over here.
Because I'm too tall. Sorry. My name is Richard Susilo from Indonesia Media. Tribun News is the largest in Indonesia. Thank you for the explanation for Sensei Sakaguchi Sensei and also Kitagawa Sensei. Very simple question. Especially for Sakaguchi Sensei, your innovations, I'm not a medical or chemical, I don't know about that one. So practically, you mentioned here, your invention could become as the drugs for the anti-immune disease, allergy, blah, 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 blah. Is there a pharmaceutical manufacturing that approach you to make this kind of drugs, whatever such? Because on the explanation of Kitagawa Sensei, he already made the atomies and cooperation with Nippon Fuso, Ohara. This is the practical things of the innovation, QB10, Daikin. But how about you, Sakaguchi Sensei? And if there is a drugs made by your innovation, is there a side effect of these drugs for human being? Thank you.
Well, so now many big farmers, they are very much interested in targeting Treg to control immune responses. For example, if you have invent monoclonal antibody targeting regulatory T cells and then reducing their number, it is good for the cancer immunotherapy. So such monoclonal antibodies are under clinical trials now. And also we hope that the small molecules, orally taken drug, which can have the same effect as immune enhancing effect in cancer immunotherapy. And that is one thing we are now working on. And then also by expanding Treg, for example, by a certain small molecule which can stimulate Treg to expand, then you can prevent allergy or other immunological diseases. And so lots of possibilities. And then there are now lots of interest in this suppression specialized T lymphocyte. And then, as you mentioned, if you reduce Treg, cancer immunity can be enhanced, but at the same time, you may see some the autoimmune diseases. So how we can separate these two events? So that is very much the people are aware of that. And then now recently, it is under clinical trial that certain monoclonal antibodies which can deplete Treg in cancer tissues, but not in healthy tissues. So that we hope that the anti-cancer immunity can be enhanced without autoimmunity or other inflammatory diseases. So that kind of direction maybe I think it's important for as a future direction of this of the research.
Thank you.
Okay, I saw this hand first and then Tim.
Thank you very much to both of you. I'm Kenji Kawase from Nikkei. My question is on the environment that which creates innovation. My question is, countries that has a free speech, freedom of thought, liberty was supposed to have more innovation. Maybe that's the reason why you go to the United States, country like United States, where you get more Nobel laureates from Europe. What about China? What is your view on China? Because a number of scholastic papers, in terms of volume, China seems to have exceeded the whole world. But what about the environment in which they are under? Does the system of a one-party authoritarian state allows innovations? Is that really real innovation really coming from that state system? Would you please give us your thoughts, both of you, on how you see China in terms of innovation? Thank you.
Well, so as you mentioned, the China, their science is now very active, and the quality is now becoming good, well, compared with the past. And then your question about innovative research, whether this is possible under that kind of society. Well, currently, my understanding is that, well, at least in medical or biology field, the financial support from the government, a communist party or communist government, that is big and also very swift. Once something is, if they decide to support certain area of science, very efficiently the help support start. So that is good for the research area where we recognize it is important, and the more investment, the more products or results. But your question of whether the good ideas, original ideas, how whether they can develop in such a society. Well, it is difficult to say because if the opportunity is better and then more financial support, then you may have a better probability of finding something. But on the other hand, the very original idea, which is not much appreciated by the society, still you can continue to working on such ideas. Well, that is, I think that the society needs kind of diversity. For example, it's not a popular idea, not much appreciated, but certain people appreciate that, and then even if it's a small amount, but keep supporting them. But on the other hand, everybody may think that, for example, cancer should be treated, and then big investments should be there, and then government must support. Well, that's also true. So that can both the diverse and the diverse in scope and a way of supporting, and then also a way of appreciating. That is eventually more important than the just a big investment, just big support. At least in biology field, I think that's my thought.
Okay, generally speaking, on the point of view of the research funding investment, so the time is the key word. So there are three categories in the fundamental science. The second in the and the estimation-based the research fund. The third is just a private area. So depending on three categories, so the timeline, time domain is just the private area is just 5 years or something like that. and the review-based the type system is just this is including the fundamental science, but still the 5 to 6 some years. But fundamental science, the time span more than 10 years. So that means in the China now in the private area it's very strong, very rich, and the second one also. But fundamental this region, I think in the next 20 years we will see if the China invests more and more in the fundamental research, and there are many Nobel laureates maybe, but right now I'm not sure about that. Okay, very excellent scientists. There are many excellent scientists right now in China, but the very fundamental, very conceptual, and the renew the interpretation of the science in this point of view in the next 20 years, I think. But I'm not a person to predict the Chinese the future.
Okay, Tim.
Tim Horniak, freelance. Last November, both of you called for an increase in the number of scientific papers coming out of Japan. You noted that scientific papers in Japan have been declining. And I think you have been calling for better funding for science in Japan. Has the government gotten your message? What is your honest opinion of the Takaichi administration's measures so far? I think they have said they want to increase funding for basic expenses and fundamental research. What do you think of these measures? What are your expectations? Thank you.
Yes, I will answer my opinion. And just like statistics, the people just evaluate this kind of status. But the point is how next generation, young people, are active, depending on the research funds and the system, in the research system. So, and right now, the young researchers, they have no plenty of time for research. So we have to give them plenty of time for research, because right now in Japanese young scientists, they doing the many things, writing. It's not a research and the grant proposal, just writing something for the business duty, something, and education means just conduct the graduate student how to use instrument, something like that. So so we think the near future the research young scientists should have the 60% or 70% research time in the daily. So this is very important. The second one is the increase the population of the young people. Right now, totally in Japan, the population of young people decreasing. So that means it's a very competitive to get young researchers in academia. Also, the company try to get these people. So it's not a good way. So we have to increase more and more young people, in particular in the academia. So that means these good salaries, okay, good working conditions are very important for the future. The overseas, for instance, in Singapore, the salary is double or triple, more than the Japanese. So it's not a good way. So this kind of thing is very important. Of course, fundamental research increase of fundamental research funds is very important. But if we look at details, this kind of factors are very important, I think.
Well, Professor Kitagawa and I, when the Nobel Prize was announced, and then at the press conference, we mentioned that the support from the government to basic sciences, that's not enough. Well, of course, the more the better, but if you compare with, say, China or the United States, the amount of support for basic science, it's big, very maybe 10 times maybe different. But for example, the GDP almost the same with Japan and then the Germany. But if you compare between Germany and Japan, and then at least in our hands, for immunology field, then the amount of support, public support, is 1/3 in Japan compared with Germany. So, but then the national GDP almost the same. So that is something it's easy to what the government to understand what the differences are. So we are pleased that this year support for basic science it increased. Until now it is decreasing, but a bit now increasing, and we hope that the Takaichi's administration they are claiming that Japan should become stronger in science and in other maybe politics maybe, but we hope that this trend of increasing the basic support for science continue to increase. Still it's low, and if they claim that Japan should, well, technology and science technology, it's important for Japan to survive, then their investment to the basic sciences, that I think it's important.
Okay, behind Tim, yes.
I'm Kari Kaneko from 3E. I have a question for Professor Kitagawa. How is the decline in science going to affect the chemical industry and companies and its competitiveness on a global stage? Immediate results are emphasized in businesses, but I wonder if the decline in science will affect businesses in the long term. Thank you.
So just let me tell you my standpoint is just a very basic science. So so in last 20, I think 25 years ago, there are no bridge between the company and the very fundamental science. No bridge. For instance, I synthesize my compound only 1 gram, but in the company need the 500 kilogram or the 1 ton, something like that. So no way to make the transfer of these type of materials to the society. But right now, I told you there are many startups. Startups contribute to using the recipe, published papers. They can synthesize these materials in the large scale and also cost down and provide to the companies they want. So it's very quick correlations. So this time is going better and better in my case, I think. I hope this kind of the link is very important for the future. My stance, just very basic science. I don't care about that. Of course, I am very kind person to provide my information more and more, but I am not almighty person, so this kind of system is very important, even in Japan.
Sakaguchi-san, anything to add?
I'm sorry?
Do you have anything to add?
No, it's okay. Well, I hope that this kind of media people, tell the people that basic science is it's interesting, and then if you have a good result, and then you have a good evaluation, and then that is good for young people, kids, they get interested in science, and so that's something I hope the media will do for promoting science in Japan.
Okay, we have one question submitted by one of our online viewers. This comes from Rocky Swift of Reuters News. This question is this is probably for Dr. Sakaguchi. During the COVID crisis, Japan depended almost entirely on mRNA-type vaccines. And there appeared to be great enthusiasm here to expand investment and research into that field. But now with health policy changes in the US, companies like Moderna are canceling a lot of mRNA therapy research. What is your read on this situation, and what, if anything, should Japan do?
Well, so the world experienced the pandemic, COVID-19, and then, very fortunately, a messenger RNA vaccine was developed. It's not complete, lots of side effects, but still it saved lots of lives. So that is one the example of how basic science is. These researchers have many years working on RNA vaccine, but not so successful, because they used for a cancer vaccine, but it isn't effective. But now, when they turn to this technology, to the microbial disease, the virus diseases, COVID-19, it turned out to be effective. And so we believe that the basic sciences for preparing emerging the infections, just preparing in advance, that is really important. That's a good example of COVID-19. So I do believe that, it is important, and then also a bit of concerns in the United States. There are some atmosphere that that kind of science or that kind of vaccination, so look at it a bit negative. That is not so good. That's all I can say at this point.
Right. Do you both have a few more minutes to take a few additional questions?
Yeah, okay.
Further questions? Yes, right here.
Takuya Nishimura, freelance. My question is not academic, but journalistic. Nobel Committee says that about the Dr. Kitagawa's discovery as that may contribute to solving some of humankind's greatest challenges, and including four examples. One is separating PFAS, from water. Second, breaking down traces of pharmaceuticals in the environment. Third, capturing carbon dioxide. And harvesting water from desert air. Which kind of field are you most interested in? It is my question. And to Dr. Sakaguchi, and also the Nobel Committee says that this may lead to development and medical treatments from cancer and autoimmune diseases. And do you have any specific disease you are interested in, to which the regulatory T cells can work? If you have any specific personal reason, please tell us about that. Thank you.
Okay. The first, I'm very much interested in the gas, targeted gas, because it's very, very difficult to realize. For instance, in the pollutants in the water, so let me tell you the role of the porous pores. Capture, okay, and store, release. And my gas target in that case is the capture, store, and the release with low energy system. Okay, so in the pollutant, it strongly interact with the pore surface, easy to capture. So that means the well-designed the power is important. But the gas system is low energy system, you know, and the capture and store and release is very important. Just please imagine this air, only 0.004% CO2, very low concentration. How to capture it? You need to have a very strong interaction. That means very difficult to release. That you have to heat more and more. That means you get CO2 from the air, and you produce a lot of CO2. So this is a big challenge. That's the reason why I'm interested in this.
Well, so which diseases can be targeted by as Treg targeting therapy? Well, what we've done is that the Treg, regulatory T cells, they are present in our body, in everybody. And then by just increasing them or reducing them, it's a kind of a very physiological way of immune regulation. And so that is one reason that the future direction of the medical treatment targeting such cancer or autoimmune diseases or allergy, well, that can be achieved by targeting Treg. So my personal interest now is one is cancer. It's a big issue, and you may know that in 2018, the Nobel Prize was awarded to Jim Allison and Tasuku Honjo. And then they invented the monoclonal antibodies for cancer immunotherapy. But it's not enough. Its effectiveness is 20 to 30%, not cure. So a lot of things to do to improve the cancer immunotherapy. So we believe that the reducing regulatory T cells in cancer tissue to enhance tumor immunity combined with the current immune checkpoint blockade cancer immunotherapy. And then if we can treat cancer, say 40 or 50%, that is a good benefit for society. So that is one the direction we'll take. And the other one is just opposite, how we can expand or increase the Treg to treat the various immunological diseases, and also prevent organ rejection in organ transplantation. So we believe that there are lots of possibilities, and we hope that the pharmaceutical companies or medical scientists they have more interest in this population of lymphocytes, and then for medical for the clinic.
Okay. I think we'll throw this open to questions from the general audience. Any non-working press members here have questions? Yes, Richard? You're getting your second question.
Yeah, sorry,
Thanks
for
for waiting.
only 1 minute. No, 1 second. On what extent, in what extent, the AI, ChatGPT, whatever, the benefit for you, both Sensei Sakaguchi and Kitagawa Sensei? Thank you.
And in my case, in the morph materials, already the more than 100,000 morph materials have been synthesized. So we have a lot of data, and using AI, we can accelerate our to producing the morph materials. But new idea, new difficult things is very difficult. AI is only just summarize the just current data. So right now we expect the acceleration of our research.
Well, my use of AI is a very usual one. I mean, looking for the literature or information, it has already been accumulated, So that's very convenient. So it makes us easier to write the papers. But on the other hand, the way of thinking or how you can make your own logic to make your paper more interesting to the readers. Well, that is different from AI. AI is convenient for just gathering the information, but it's different from the thinking about something new. So that's our experience, and and also my beliefs. So AI is convenient, and then we must become good at using them. But just like a cellular phone, it's convenient, but also it has a some young people are kind of toxic or intoxicated, whatever. So indulging in the AI is not good, but it is useful, and then we must master to use it. So that is we are required to do. That's my belief.
Thank you. Okay, on that note, I think we will wrap this up. As moderator, I get the last word, and I'd like to thank both of our guests for coming here today, Dr. Kitagawa and Dr. Sakaguchi. And as a token of our appreciation, I have 1-year honorary memberships for both of you to the FCCJ. We hope you'll come back and see us again. Thank you.
Thank you very much.
And thank you all for coming, and thanks for the questions.